Today we're doing section 7.2, quadratic forms. Quadratic form. A quadratic form on Rn is a function q defined on Rn whose value at a vector x in Rn can be computed by the expression of the form q of vector x equals x transpose A times x, where A is an n by n symmetric matrix. Matrix A is called the matrix of the quadratic form. Let's go ahead and look at example 1. Let x be x1, x2. Compute x transpose A of x for the following. So for A, we're going to compute x transpose A of x, which would be x1, x2. A would be 4, 0, 0, 3. x1, x2. We're going to multiply these two matrices together first, 2 by 2 and 2 by 1. So our x transpose will stay here. And when we multiply those, you get 4x1, 3x2. And when we multiply these, we get 4x1 squared plus 3x2 squared. Notice there's no cross product term, and there is none because the diagonal is 0, 0. So notice there's no cross product term. Let's go ahead and do the same thing for letter B. So first I'm going to multiply the 2 by 2 and the 2 by 1 and get 3x1 minus 2x2, negative 2x1 plus 7x2. Then I'm going to multiply these, and I get x1 times 3x1 minus 2x2 plus x2 times negative 2x1 plus 7x2. Go ahead, distribute, and you'd get 3x1 squared minus 2x1 x2 minus 2x1 x2 plus 14x2 squared. No, plus 7x2 squared. My bad. This would then be 3x1 squared minus 4x1 x2 plus 7x2 squared. Notice we have a cross product term. So here is our cross product term, and that's because the diagonal is not zeros. Example 2. Let q of x equal x1 squared minus 8x1 x2 minus 5x2 squared. Compute the value of q of x for x equals negative 3, 1, 2, negative 2, and 1, negative 3. So we're going to first do it for q of negative 3, 1. And we would just be plugging those in. So I'd have negative 3 squared minus 8 times negative 3 times 1 minus 5 times 1 squared, which equals 28. Q of 2 negative 2 equals 2 squared minus 8 times 2 times negative 2 minus 5 times negative 2 squared, which equals 16. And Q of 1 negative 3 would be 1 squared minus 8 times 1 times negative 3 minus 5 times negative 3 squared, which gives me negative 20. In some cases, quadratic forms are easier to use when they have no cross product term, when the matrix of a quadratic form is a diagonal matrix. Cross product terms can be eliminated by making a suitable change of variable. So, change a variable in quadratic form. If vector x represents a variable vector in Rn, then a change of variable is an equation in the form x equals p vector y, or y equals p inverse vector x, where p is an invertible matrix and y is a new variable vector in Rn. Here y is the coordinate vector of x relative to the basis of Rn determined by the columns of p. If the change of variable is made in quadratic form, A transpose A of x, then we have this. And the new matrix of the quadratic form is P transpose AP. If P orthogonally diagonalizes A, then P transpose equals P inverse, and P transpose AP equals P inverse AP, which equals D. The matrix of the new quadratic form is diagonal. Let's look at, it says example 3, but really example 2. Make a change of variable that transforms the quadratic q of x equals x1 squared minus 8x1 x2 minus 5x2 squared into a quadratic form with no cross product term. So with this, we have, I'm going to rewrite down my q of x. This equals 1x1 squared minus 2 or plus 2 times negative 4 x1 x2 minus 5 x2 squared. So here, this negative 4 are the corners of our matrix. And this 1 and negative 5 is our diagonal. So our matrix A is now going to be 1, negative 4, negative 4, negative 5. We need to find our eigenvalues. To that, remember, determinant of A minus lambda I equals 0. So the determinant of 1 minus lambda minus 4, negative 5 minus lambda equals 0. So I'd have 1 minus lambda times negative 5 minus lambda minus 16 equals 0. When I multiply this out, I get lambda squared plus 4 lambda minus 21 equals 0. Lambda minus 3 times lambda plus 7 equals 0. So my lambdas are 3 and negative 7. So now we need to find the basis for lambda equals 3 and lambda equals negative 7, then normalize those vectors. So we're going to start with lambda equals 3, and that's when we're going to solve a minus 3I x equals 0. So my matrix would be negative 2, negative 4, negative 4, negative 8. the first thing I can do is I can zero out the bottom row by adding -2 times the first row. And then I can divide the first row by -2. And I end up having x equaling -2x2 and x2. So x would be x2 times -2, 1. So v1 equals -2, 1. And we need to normalize that. And when you do, we're just going to do it here. We get u1, which is 1 over the square root of 5. Times -2, 1, which equals -2 over the square root of 5. And 1 over the square root of 5. We're going to do the same thing for lambda equals -7. So we're going to solve a plus 7 lambda times vector x equals 0. So I'd have 8, -4, -4, 2. First thing I can do is I can take half of row 1 and add it to row 2 to zero that out. And then I can divide row 1 by 8 to get 1, 0, -1/2, 0. So x would be -1/2 x2 So x would equal x2 -1/2, 1. So v2 equals -1/2, 1, 1. We have to normalize v2, and when we do, we get 1 over the square root of 5 times 1/2, 1, which equals, or times 1, 2. And we get 1 over the square root of 5 2 over the square root of 5. So the associated unit eigenvectors are these, and these are the associated unit eigenvectors. So they automatically are orthogonal because they correspond to distinct eigenvalues and provide an orthonormal basis for R2. So we're going to let P equal -2 over the square root of 5, 1 over the square root of 5, 1 over the square root of 5, 2 over the square root of 5, and D equal 3, 0, 0, -7. And then AP D P inverse and D P inverse AP equals P transpose AP. which is a suitable change of variable, is as follows. So vector x equals py, where x is x1, x2, and y is y1, y2. Then x squared 1 minus 8x1, x2 minus 5x squared, x2 squared equals x transpose a of x and x is the same as p times y, so py transpose a of py this would be the same thing as y transpose p transpose a py and p transpose AP equals D. So we have y transpose D y. And that would be 3y 1 squared minus 7y 2 squared. So let's look at theorem 4. The principal axes theorem. Let A be an n by n matrix. Then there is an orthogonal change of variable, x equals py, that transforms the quadratic form x transpose ax into a quadratic form y transpose dy with no cross product term. The columns of P in theorem 4 are called the principal axes of the quadratic form A transpose AX. The vector y is the coordinate vector of x relative to the orthonormal basis Rn given by these principal axes. So a geometric view of principal axes. Suppose Q of x equals x transpose AX, where A is an invertible 2 by 2 symmetric matrix, and let C be a constant. It can be shown that the set of all x and R2 satisfies x transpose A of x equals C, either corresponds to an ellipse or circle, a hyperbola, two intersecting lines, or a single point, or contains no points at all. If A is a diagonal matrix, the graph in standard position, such as in the figure below, if A is not a diagonal matrix, the graph of the equation is rotated out of standard position as in the figure below. Classifying quadratic forms. A quadratic Q is a positive definite if Q of x is greater than 0 for all x not equal to 0. It's negative definite if Q of x is less than 0 for all x not equal to 0. It's indefinite if Q of x assumes both positive and negative values. Also, Q is said to be positive semi-definite if q of x is greater than or equal to 0 for all x, and negative semi-definite if q of x is less than or equal to 0 for all x. Theorem 5, the quadratic forms and eigenvalues. Let A be an n by n matrix. Then a quadratic form A transpose A of x is a positive definite if and only if the eigenvalues of A are all positive. A negative definite if and only if the eigenvalues of A are all negative. Indefinite if and only if A has both positive and negative eigenvalues. Let's look at example 4. Is q of x 3x1 squared plus 2x2 squared plus x3 squared plus 4x1 x2 plus 4x2 x3 a positive definite? So because all positive looks positive definite. So it looks positive definite, but we don't know. So first, let's define our matrix A. So the first 3 here that I'm going to put that are all squared go down the main diagonal. So there's a 1 here. And then this will be split evenly. And this will also be split evenly in the matrix that I'm going to have down here. So we're going to start with our diagonal. So we have 3, 2, 1. That first 4 that I have in pink is going to be split evenly first. The last 4 is going to be split evenly here. And then since I don't have any constant terms, those would be 0. So you need to find the eigenvalues, like we did in the previous example. We're not going to go through that process again, but you should get, and if you want to try and practice, lambda equals 5, 2, and negative 1. So Q is an indefinite quadratic form, not positive definite. And that's because we have both positive and negative values.